Hi, thank you for your interest in our work on supervised zero-shot segmentation using Stable Diffusion. To achieve unsupervised zero-shot segmentation, we utilize the image encoder in a pre-trained diffusion model. The UNet encoder consists of a stack of downsampling and upsampling blocks. Most of the blocks have transformer layers with attention mechanisms. As shown in this figure on the right, all blocks with a solid boundary have a transformer layer. They will generate four-dimensional attention tensors. Our segmentation method, Diffseg, consists of three components: attention aggregation, iterative immersion, and non-maximum suppression. A diffusion model produces attention tensors of different resolutions. Our goal is to aggregate all attention tensors to the highest resolution. The process consists of two steps. The first step upsamples the last two dimensions, and the second step duplicates and arranges the first two dimensions. In the end, the attention aggregation component returns a four-dimensional tensor of resolution 64 by 64 by 64 by 64. The second component is iterative merging. To start the merging process, we first sample some anchor points. Diffseg constructs an m by m sampling grid, and each point in the grid corresponds to an anchor point. We obtain the two-dimensional attention maps at those anchor points by indexing into the first two dimensions of the aggregated attention tensor. The sampled attention maps form a list of anchor attention maps, and this gives us m squared number of attention maps, serving as our anchors. Then Diffseg performs n iterations of merging. Specifically, the merging process has three steps. First, it calculates the similarity between a specific attention map and all other maps. Then it merges attention maps with high enough similarity. Finally, the merging process is done without replacement, therefore reducing the number of remaining attention maps. The merging process will significantly reduce the number of attention maps. In the end, we'll be left with only k attention maps, which we call probabilistic object proposals. They capture distributions of distinct object groups. For example, after iterative attention merging, we obtain four object proposals for this example. The merging process uses specific similarity criteria. Because attention maps are valid probability distributions, we can use distance metrics for probability distributions to measure similarity between attention maps. In this paper, we use KL divergence. Specifically, we use a combination of forward and inverse KL divergence because KL divergence is an asymmetric measure of distance. A smaller KL divergence indicates higher similarity. The last component is non-maximum suppression, which turns the probabilistic proposals into valid binary masks. We first upsample the object proposals from 64 by 64 to 512 by 512, which is the resolution of the input image. Then we take the argmax across the first dimension to assign each pixel to the proposal with the maximum probability, and the result is a valid segmentation. To recap, Diffseg has three main components: aggregation, merging, and suppression. The entire segmentation pipeline purely operates on the self-attention maps from a stable diffusion model. To extract the attention maps, we run a clean image through a diffusion model only once. Quantitatively, Diffseg significantly outperforms prior works. All prior works require additional resources for segmentation, such as auxiliary images, language assistance, or training on the target dataset. Diffseg is the only work that does not require any additional information training on the target. More significantly, it outperforms prior works by 57% in mean IOU. Qualitatively, Diffseg can segment a diverse range of images. For example, these are sketch images from DomainNet, paintings from DomainNet, real door images from the Sun RGBD dataset, real outdoor images from the Coco Stuff dataset, images captured by a smartphone. Of course, Diffseg can segment generated images. This concludes our overview of Diffseg. Feel free to check out the paper and the project page. Thank you for listening.